Hello everyone, I am Zach Peterson. Welcome back to my channel. Today we're going to be talking about something that is very important when defining footprints, especially for BGAs, and that is the difference between solder mask defined pads and non-solder mask defined pads. This topic came up from a viewer comment on one of my other videos, and I thought it would make a great follow-on, and so we're talking about it today. Let's go ahead and jump in and look at that viewer comment, and then we'll discuss the difference between these two types of pads in BGA footprints. So the topic of today's video is non-solder mask defined pads, or NSMD, versus solder mask defined pads, or SMD pads. Let's take a look at that viewer comment that spawned this video. Sean3994 writes, another thing to consider with via in pad, specifically relating to BGAs, is the use of mask defined versus pad defined. Because the solder mask opening around BGA pads generally has a larger radius than the copper pad, an oversized via pad in this location will result in more copper area under the ball. The part will not generally have vias under all the balls, and this will effectively present different sized pads to the part, and that can cause attachment issues. By adjusting the solder mask, this issue can be removed. This is a really great point, and I think this Sean is actually Sean Kincaid, who was one of the guests on the Altium podcast and who has also made a really great video about our design reviews. But this is a really great point to bring up about BGA footprints, especially as it relates to via in pad, as you get to smaller and smaller pad pitches in the BGA footprint. As you get to a smaller pad pitch in your BGA footprint, what happens with via in pad is the pad oversize on that via that's required to maintain the required annular ring could be so large that it pokes underneath the solder mask opening around that pad in your BGA footprint. And that's what creates these different exposed pad sizes in that BGA footprint, thus potentially causing the attachment issues. So what we need to do is figure out the right amount of copper that we need to expose in the BGA footprint in order to ensure consistent attachment across the entire BGA component during assembly. To do that, we can take a look at some of the IPC standards that help us determine the right pad size that we can use. So let's take a look at this article I have on screen on the Altium blog. Now, I've shown this article many different times because it contains the information that you need to properly size pads for your BGA footprint. So if you just go to this article, and I have the link in the description, you can scroll down here to these two tables that are taken from the IPC 7351 standards. The IPC 7351 standard contains data that gives you a land pad diameter for a BGA footprint as a function of the ball diameter on the bottom side of the BGA. So here I have one table for collapsing balls, and then there's another table here for non-collapsing balls. Now, most BGAs will have collapsing balls, so most likely for the parts that you might be using, this is the table that you're going to want to use. Now, the ball diameter can generally be found in the mechanical drawing for the component that you're working with. And all you need to do is look at the ball diameter, scroll over here to the land diameter, and that's going to be the landing pad that you want to use for your component. For a 1mm pitch BGA, which tends to be at the large end of the BGA components most people use, you're going to have a larger ball diameter, typically 0.65 millimeters, and that requires a nominal land pad diameter of 0.5 millimeters. So that 0.5 millimeter land diameter is the amount of copper that we need to expose to the balls on that BGA during soldering. How does this relate to solder mask and non-solder mask defined pads? Well, let's hop onto the whiteboard and we'll see exactly what these pads are and how they relate to the data in this table and how this all relates to via in pad. So now let's look at solder mask defined and non-solder mask defined pads, and we'll do this again for our hypothetical 1mm pitch BGA footprint. So in this example, we're going to have some pad that is going to be used for soldering the BGA, and according to the 7351 standards, this should basically be about 0.5 millimeters in diameter. Now, this is the exposed copper, and if this is the actual size of the copper pad, in order to ensure that we always have this much copper exposed for soldering, we would then apply a little bit of solder mask expansion around this pad in our CAD tool. Typically, the oversize on this solder mask expansion is going to be, let's say, 1 mil. And that 1 mil or maybe even 2 mil of opening is going to allow for some misregistration tolerance when the solder mask is applied on the surface layer of the PCB. So even though there will be a little bit of misregistration in the location of this solder mask opening, that's going to ensure that you always have 0.5 millimeter diameter pad exposed to the bottom side of that BGA for soldering. Now, because the size of the pad is defined by the pad size itself, we call this a non-solder mask defined pad. Now, the other way to define one of these pads is to actually use the size of the solder mask in order to set the size of that opening. So if we have a solder mask defined pad, instead what we do is define an opening of, in this case, 0.5 millimeters in diameter, and then we set the size of the copper to be anything larger than 0.5 millimeters. So now the size of the opening here is what defines the amount of exposed copper that the BGA will solder onto. And so this is called a solder mask defined pad, or an SMD pad. Now there will be some distance between the edge of the solder mask opening and the edge of the copper pad that's hidden by the solder mask. But we don't typically set this to some value like exactly 1 mil or 2 mil. We can kind of set the copper pad size to be whatever we want. All that matters is that we leave enough copper exposed through this solder mask opening, and we have that consistently across the entire BGA footprint in order to ensure consistent soldering of that BGA onto the PCB. Now typically with a 1 millimeter pitch BGA, we aren't actually doing any of this because we're not doing via in pad. The reason is that if you look at a typical PCB layout that has a 1 millimeter pitch BGA, you will see that the fan out is actually dog bone fan out. And that's where the vias are offset from the pads and they aren't actually sitting in the area where solder is going to hit onto these landing pads. So with a 1 millimeter pitch BGA, or possibly even a 0.8 millimeter pitch BGA, all you need to do is just set the right pad size, set a little bit larger solder mask opening, not too large but not too small, and then you'll be able to do dog bone fan out, and you won't have to worry about any of this stuff to ensure that you get a consistent copper exposure to the underside of the BGA for soldering. So now to see a case where we might need solder mask defined pads, we would need to look at a case where we have via in pad in the BGA footprint. And so that's where we're going to look at a finer pitch BGA, such as a 0.65 millimeter pitch BGA. Now this is kind of a mid-range pitch size where it's not so tight that you have to do micro vias, but it's not large enough to do dog bone vias. Now you probably could do dog bone via fan out using micro vias, but that's a little bit going overboard. You could still do mechanically drilled vias in this footprint using solder mask defined pads. So in this pad pitch, our pad size is going to be, for example, 0.3 millimeters. So that's our pad diameter. And then we're going to have another pad down here, which is also 0.3 millimeters. Now, if we just calculate the edge-to-edge clearance between these two pads, we're going to pretty quickly see that this distance here is 0.35 millimeters. Now, these numbers are really important because if I want to use mechanically drilled vias in these pads, what am I going to have to do? Well, I'm going to have to ensure that I have enough annular ring around that drill in order to comply with IPC standards. So if I wanted to use even the smallest drill diameter of, let's say, a 6 mil drill or a 0.15 millimeter drill, that's going to require at least 8 mil of pad around that drill in order to meet IPC Class 2 standards, and that's assuming that our fabricator is operating at the highest producibility level. Now, not all fabricators are operating at that level. Some fabricators might require a 10 mil oversize, giving you a 16 mil pad that you would have to place around this 6 mil via in order to comply with IPC Class 2 standards. Now, you should notice right here that we can't just put a 6 mil drill into a 0.3 millimeter pad because 0.3 millimeters is only 12 mil. So we wouldn't have enough annular ring around that 6 mil drill in order to comply with IPC standards. That would mean that this BGA pad size actually needs to be about this big, or 16 mil. And again, that's assuming that you're operating at a typical producibility level at your fabrication house. Now this 6 mil drill in this pad may not actually be practical at all, because if you have a standard thickness board and you're trying to do a through-hole via at 6 mils, that's going to require a 10:1 aspect ratio on those holes. That 10:1 aspect ratio at a 6 mil drill is usually larger than what a lot of fabricators will guarantee in their processing capabilities. Typically, they'll only allow an 8:1 aspect ratio with a 6 mil drill. So that might force you to instead use an 8 mil drill diameter. And if they require a 10 mil pad oversize, then that sets your pad size to 18 mil. So you can already see that when you have these thicker boards with a lot of pins on a very dense BGA, that's forcing you to use these larger mechanical drills. And that increases the pad size that's required for these vias around this exposed copper requirement based on this BGA pitch size. So what should we do in this situation? Well, here in this situation, if we're putting these large pads that we're using for via in pad, we might end up having a smaller clearance right here between the copper pad edges. And that's okay. This copper pad edge clearance could be down as small as 4 mil if we need it to be. But what we would want to do is we would want to set the solder mask opening in this case to be equal to the pad size, or the copper amount that we need to expose to the bottom side of the BGA for soldering. So this is where we're using solder mask defined pads on these BGA pads or on these via pads in order to define the amount of exposed copper that will be given to the BGA during soldering. Now this is typically why in a lot of footprints for fine pitch BGAs, you can't actually just apply your global solder mask opening rule in your CAD tool. It's going to oversize some of these pads compared to other pads in the BGA footprint. For example, if we had a 1 mil solder mask expansion as a global rule in the entire BGA footprint, then any footprints that had via in pad would have a solder mask opening that is just a little bit larger than these other pads that don't have any vias in them. So if I have a pad over here, let's say, it's going to have 0.3 millimeters or 12 mil of exposed copper, whereas this pad will have 14 mil of exposed copper. So the solution in this case, where you have a finer pitch BGA and you have some of your pads with via in pad, but some pads don't have any vias in them, you want to set the solder mask opening equal to the amount of copper that needs to be exposed for soldering this BGA onto the PCB. To do that, you can oversize this copper just a little bit and then apply a small negative mask expansion in order to account for solder mask misregistration tolerance. Now I've talked about solder mask expansion many times. I've shown examples of bad solder mask expansion applied automatically in design reviews, and I've talked about it a little bit on finer pitch components like QFNs and QFPs, and even some examples with BGAs. But once you get to these finer pitch BGAs like a 0.65 millimeter BGA, you definitely want to apply a larger pad and then a negative mask expansion, have an SMD pad to ensure consistent soldering everywhere across that BGA footprint. Thank you very much, Sean, for that awesome comment, and thank you very much everybody out there for watching this video. And as always, if you have a great comment or question, you can leave it in the comments section and it just might end up in one of these videos. Make sure to hit the like button, hit the subscribe button, and I'll see you next time, folks.